All right, this presentation will work through the homework for lesson 8-4, vectors in three-dimensional space. So our first few problems are simply sketching, and we are given the point 1, -2, -4. And as a reminder, that is your x, that is your y, and that is your z. So when we think about this three-dimensional graphing grid, this Cartesian type grid, we're going to have our x, our y is going to go to the right, and our z will go up. So if you think z to the north, y to the east, x to say maybe the southwest might be a way to picture that, but those three lines are the main ones you need. Sometimes I'll capture these lines, the negative y as a dashed line, maybe the negative x as a dashed x, and the negative z as a dashed z. And that just helps me to highlight the x and the y and the z. You don't have to do that. They didn't do that here in this example, but it could help. Different colors can really help you map these out as well. And so we want to go one right here in the x, and then we're going to go to the left 2, which means we have to go along the y-axis 2 units to the left. But notice how this line is parallel to the x-axis. This line here is parallel to the y-axis. So we're mapping it here, and then we go down 4. So 1, 2, 3, 4. All right, down 4 in the z. And so my dot is right there. And we can really map this. They've mapped this as a three-dimensional, really just parallelogram here, rectangular figure. But that's where the dot is. That's the coordinate 1, -2, -4, -5, -4, -2. And so we would go -5 in the x, which is back here, -4 in the y, and then down 2 in the z. And so this is the point -5, -4, -2. For 5, we are going to go -5 in the x, 3 in the y, and then up 1 in the z. And so hopefully by them drawing in these dashed lines, you can get a visual of the rectangular solid that would be here and just how this point is in reference back to the origin. All right, so for number 9, they gave you the instructions to find the length and midpoint of the segment with the given endpoints. So this is the same thing we've been doing in a previous unit. We're just having the z-axis thrown in. And so we're going to use our distance formula where we 1 minus, we're going to x2 minus x1, y2 minus y1, and z2 minus z1. We're going to square all those, take the square root, that's root 150. So the length of this of these two vectors, 12.2. The distance between these 2 points, I should say, is 12.2. What is their midpoint? We're going to add the 2 units, and I wrote x2, x1 because I had the x2 minus x1. It's really x1 plus x2, but it doesn't really matter because you're just combining numbers. And so the midpoint coordinate would be -3/2, 5, and 13/2. So for 11, I'm going to apply the same formulas, both the distance formula for the length and the midpoint formula for to calculate, well, the midpoint. And so I'll let you pause the video and look at those numbers. 13, another problem, just the same, distance formula, midpoint formula. You can pause the video and see the math work there. But now let's go to 15. Looks a little different, but not really. And so for 15, we have a family, they're in Kansas, and these are their home coordinates, and they're going to, where was it? Castle Rock, Colorado, and these are the coordinates there. So there's an X and a Y and a Z. Notice the different units for the Z. Okay, so this is like latitude, longitude, but then we're dealing with our Z's, our elevation. And so we just want to know the halfway point between their home and Castle Rock, Colorado. Just use the midpoint formula. Don't let the degrees or anything fool you. It's 37.7 plus 39.4 divided by 2. And that's all you do. And so these are the coordinates, latitude, longitude, and elevation, halfway between their home and Castle Rock, Colorado. All right, so let's look at 25. 25, find the component form and magnitude of vector AB with the given initial terminal points, then find a unit vector in the direction of AB. And so if we want to break this down into component form, we're going to say x2 minus x1, y2 minus y1, z2 minus z1. and there's your component form. And so it's the same as we've done previous. We're just adding the z component in. Now we want to determine the magnitude. So you know how to do that. 16 squared plus 2 squared plus 8 squared, that's root 324. That's a perfect square. So the magnitude is 18. And you'll remember this, I believe it was in the last lesson. If we want a unit vector going in the same direction, we take the component form of the vector and divide by the magnitude of the vector. And that results in 8 over 9, 1 over 9, and 4 over 9. So that's going to be a unit vector in the same direction as the initial vector. Let's look at 26, more of the same. They give you two new vectors. We're going to put that in its component form. We're going to solve for the magnitude and reduce the 208 to 4 root 13. We could also set that magnitude as 14.4, but the 4 root 13 helps us in the next phase when we're calculating a unit vector in the same direction because it cleans this up a little bit. We don't want to be dividing by 14.4. We want to divide by something more exact, like 4 root 13. We'll get the radical out of the denominator and simplify, and you end up with this unit vector that runs in the same direction as the initial unit vector. All right, 36. Here we're just doing operations with three vectors. So they provided us three vectors, A, B, and C. And the first one is 6A minus 7B plus 8C. This is really the same as we did in the last lesson. We're going to distribute. We're going to first substitute the vector in for A, and for B, and for C. Distribute the coefficient on the outside. Make sure you watch your signs. And then add accordingly. And so this is that resultant vector, negative 88, 6, and 99. We're going to do the same thing in 37, which is 7A minus 7B. All right, let's look at 48. This was the last problem. We've kind of cruised through this homework. Hopefully this one didn't frustrate you too bad, but let's slow down just a little and take a look at it. So this is my sketch of the drawing. Now they've got a better one in the book, but I think this is fairly helpful. We're going to have, you can see how I've taken my X and then my west-east coordinate, and here's the y-axis, the north-south, and then here's my z straight up and down. And so here's the plane. It's heading north, it's heading due north, but it's at an angle of elevation at 20 degrees. But the wind is coming in from the southwest. That means it's heading in a northeasterly direction. And remember, when they say southwest, northeast, that's at a 45-degree angle. So they're splitting the difference between west and south, north and east. And we know that that's happening at 8 miles per hour. All right, so the first step is to break each of the vectors, the given vectors, and we have the wind and we have the airplane. So let's start with the airplane. We want to break it down into its component form. We know that it is 20 degrees. That's my angle. So if you can picture, if I just drop a vertical, I've just created a triangle, haven't I? And so I know my internal angle. 150 miles per hour is going to be the hypotenuse, and so I need my vertical, which is my sine. I need my horizontal, which is my cosine. So cosine of 20 equals x over 150, and the sine of 20 equals y over 150. Solve accordingly, and this is the tricky part right here. Think about what you're solving for. Where did this zero come from? Remember, the north axis, I said the north-south axis is my y-axis. So when I calculate a cosine for this, that's my y component. All right, that's why it goes here. 150 times the cosine of 20 is 140.95. What about my x? The x is the east-west, but the plane's heading due north. And we're going to assume that due north means due north. There's no westerly or easterly slant to it. So that number is 0, okay? 51.30, where did that come from? So 150 times the sine of 20 is 51.30. And that, when I do my vertical here, look at that, that's parallel to the z-axis, isn't it? So when I calculate the sine, if that's the axis it's parallel to, I've got to put it in for my z. Now break down the wind component, I labeled it W, into its components. And I'm left with cosine of 45 is going to be an x and a y, right? So I got to go to the sine and cosine of 45. So 8 cosine of 45 is 5.7. 8 times the sine of 45 is also 5.7. And then it's the z that's 0 because we're assuming this wind to be like just horizontal. We're not giving like a three-dimensional or up or down per se to the wind. It's coming across the ground straight. And so there's not going to be a z component. So now the resultant vector, and I've called that r, is equal to p plus w, the component form of p plus the component form of w. And so here are my two vectors. So when I add them together, 0 plus 5.7 is 5.7, 140.95 plus 5.7 is 146.7, and then 51.3 plus 0 is 51.3. You could also write that in the form of ijk as seen below. But that's the resultant vector with the plane at a 20-degree angle headed due north at 150 miles an hour with a wind coming out of the southwest at 8 miles an hour.